Hi guys, today we're talking about classical and relativistic momentum of a proton. So in this problem it says apply physics to find the classical momentum of a proton traveling at 0.976 the speed of light. Repeat, but now find the relativistic momentum and see does it make sense to neglect relativity at such speeds. And just in case you're wondering, this picture is a picture of protons colliding in the Hadron Collider. Anyways, so for the first one, it's really quite simple. As you know, classical momentum is just P, which is your momentum, equals mass times velocity. So we just take the velocity, which it's going at 0.976, the speed of light. So you take 0.976 times the speed of light, which is 2.9979 times 10 to the 8th meters per second. Okay, and you're going to multiply that by the mass of the proton. And the mass of a proton is going to be 1.67265 times 10 to the negative 27th kilograms. Alright, so let's switch over to the calculator. So we've got 0.976 times speed of light, which is 2.9979 times 10 to the 8th. Okay. And then we're going to multiply that by the mass of the proton, which is 1.67265 times 10 to the negative 27th. Okay, and we get 4.89 times 10 to the negative 19th. Okay, so the answer for A is going to be 4.894 times 10 to the negative 19th kilograms times meters per second. All right. Now for part B. Okay, so for part B, it says repeat, but now find the relativistic momentum. So we're going to be using this equation. So you're just going to take the same thing right here. So let's just draw this out. Alright, and you're going to take this whole part, because this is just your mass times velocity, mv, right here. And so you're going to take that, this whole deal, and you're going to stick it up here. Alright, and for the bottom part, we're going to take the square root of 1 minus velocity squared times c squared. So we know the velocity is 0.976 of c, and so that's going to be squared. So you're going to put 0.976 c, right, squared over c squared. Well, if you were to break down these parentheses, we know that this is the same as, let's just do this real fast. It's the same as, hang on one second. Okay, we know it's the same as 0.976 squared and c squared. Alright, so when you do that, you can get rid of that c squared, and you're left with 1 minus 0.976 squared. Okay, And of course, you're still going to have your top part. So let's go to the calculator. So we've got this top part, which is 0.976 times 2.9979 times 10 to the 8th. Now, of course, you could have just took this answer and put it in there, but I like to try to be as specific as possible. There's only 6 digits here because the calculator is only floating 6 digits, but there would actually be more. Okay, so then you're going to multiply that by the mass, 1.67265 times 10 to the negative 27 kilograms. Okay, and then we're just going to put this whole deal in parentheses just to be on the safe side. And then for the bottom part, we're taking the square root of 1 minus 0.976 squared. Okay, and we get 2.25 times 10 to the negative 18th. Alright, so for B we get sorry about that. 2.25 times 10 to the negative 18th kilograms times meters per second. Alright, so okay, so for C, does it make sense to neglect relativity at such speeds? And well, it might seem that these answers are pretty similar, 4.894 times 10 to the negative 19th and to the negative 18th. You know it's going to be really, or these momentum, I'm sorry, the momentum is, I mean, the numbers are very similar. But if you were to try to figure out how much more momentum when you use the relativistic equation do you get over the classical equation, you're simply going to take the answer from what you get here over P. And this is going to give you a factor. Okay, so let's do that. So we've got, here we'll just do this. The answer, and that's just going to give us this 2.24736, and then, okay, so you're going to take that and you're going to divide it by this 4.89, 4.8940 times 10 to the negative 19th. 10 to the negative 19th. Okay, and it's going to give us a factor of 4.6 roughly. Alright, so that is actually quite a difference. 4.6. Alright, so that is actually quite much larger. The momentum of the proton using the relativistic equation is going to give you 4.6 times more momentum than using the classical method. And that is how you solve that problem.